All right, we're on to lesson 2 for chapter 10. We're still working through the first section of the textbook, looking at angles in a circle, but we are going to move to our third circle property. So last lesson looked at inscribed angle property and central angle property, and this is going to look at angles in a semicircle. If you are someone who struggled with Pythagorean theorem last year, I've added a couple links to some Khan Academy videos that I would like you to watch, as well as a playlist of some practice questions that you could do on Khan Academy for extra practice. I am expecting that you know it and you're comfortable with it. So if you struggle, do that practice or come see me in tutorial for some extra help. Okay, first example is a review of the ideas from lesson 1. So I'm not going to do that with you, but we'll check it over together in class tomorrow. We're going to move here. Angles and semicircles. So we had one example at the end of the first lesson that looked at this, but I'm going to remind you of this again, that any angle formed over a semicircle will always be equal to 90 degrees. So it'll always form a right angle. And so I want you to think of this circle if it was continued. I know that I just drew a very boxy circle, but imagine. And so this is the center of the circle. And so this is the diameter. And so the central angle is a diameter line with endpoints at the edge of the circle. Central angle. This is the minor arc, or I guess technically it could be the minor or the major. And so we have two inscribed angles that also start and end at the same endpoint, so they share the same arc. They're subtended by the same arc. So if the central angle is 180 degrees, the inscribed angle is going to be the central angle divided by 2, which is 90 degrees. And if you remember our other angle property, it said that two inscribed angles that share the same arc share the same value. So this also has to be 90 degrees. Okay, and so then if we had a full circle, we could draw this in any direction as long as we have a diameter line. If I make a point anywhere on this circle to make an inscribed angle, it will always make a 90-degree angle, assuming I have used a ruler and drawn straight lines. And if you don't believe me, my challenge to you is then to try and find a situation where that won't work. Okay, next example. Some review of isosceles triangles. And so an isosceles triangle, if you remember, is a triangle that has two equal side lengths, and so it also has two equal angles. And so the side lengths that are equal are these two. And so then these two angles would also be the same. So you can kind of think of it like each half of the triangle is a mirror image of the other. Okay, so if we said, for example, that this top angle is 40 degrees, and I said, okay, what are these bottom angles equal to? Well, we know that they have to be the same. And so another thing we need to remember is that all the angles in the triangle when all the angles of a triangle are added together, they have a sum of 180 degrees. So when you add them up, you get 180 degrees. And so we know that 180 degrees take away the 40 degrees gives us 140 degrees. And so these two bottom angles have to share that evenly. So that tells me that each angle has to be 70 degrees. Okay, so that's an important property we are going to want to keep in mind. And And again, some Pythagorean review. I will go through these two quite quickly. If this is too fast for you, please see me in tutorial, or if you're really, really lost, please look at the Khan Academy Extra Practice and see me in tutorial as well. Okay, so first thing about Pythagorean is we're talking about the square off the side lengths. And if we add the two smaller squares together, it will give us the hypotenuse, or the longer length square. A reminder for how to find your hypotenuse. So if you think of like a bow and arrow, if you think of shooting an arrow through the 90-degree angle, it is going to point at your hypotenuse. So, and then from there, however you want to label A and B, it doesn't matter as long as they're the two other leg lengths. And so if we need to find the hypotenuse, we can just use our formula. A squared plus B squared equals C squared. And remember to follow your order of operations, and you need to square the side lengths before you can add them. So we've now found the area of the square that would come off of the largest side length. But we don't want to know the area, we want to know what the side length is. And so another reminder for you is to go from the area to the side length of a square. You do not divide it by 2. You do not divide it by 4. You take the square root. The opposite of square is square root. And so that tells me that the side length is 10. You could either remember that 100 is a perfect square and it's on your perfect square table, or you could use your calculator and go square root 100. So the other type of situation you will need to remember is how to find a missing side length if you know the hypotenuse. So again, we'll shoot an arrow through, and so we know the hypotenuse. We know one of the side lengths, but we don't know the other side length. And so the way that we find this side length is taking the larger area of the hypotenuse and subtracting the smaller area. So we're going to find the difference in this case. Again, following order of operations. So 25 take away 9, b squared equals 16. And to find a side length from an area, we square root. The opposite of square is square root. So again, if those seem too fast or you had no idea what I was saying or doing, please come see me. So we're going to use what we've just reviewed to find some missing side lengths. I might ask you to do a couple of these on your own. I think it is really helpful for you to try them on your own and then have us check them together, but I'll show you 1 or 2 of them and then let you go from there. Okay, so the first one, we have a diameter line and then we have an inscribed angle. So again, using your pencil crayons or colored pens would be really helpful. Pencil crayons are a little bit better because at least then you can erase. Central angle, 180 degrees. Okay, oh, sorry, we only need the side lengths. But knowing that this is 180 degrees, and then we have an inscribed angle on the same arc, tells me that BCA is actually a right triangle. And so because it's a right triangle, I can use Pythagorean theorem. If it was not a right triangle, we could not use Pythagorean theorem. And so that means I'm going to shoot an arrow through the 90 degree to point at the hypotenuse. And so 13 is the hypotenuse. And so I'm looking for a side length. So c squared minus b squared will give us the side length. So 25 is the area coming off of A. We're going to square root it. And so the length of A is 5. So I hope that was a nice, easy little example for you. When we look at B, B is quite similar to A, so I am not going to do B. I'm going to let you try that one for yourself. Let's look at C. And so for C, there's no side lengths that are missing, but there's angles that are missing. So we need to find the missing angles for C. Let me just slide that up there. Okay, and so we have a bunch of different angles going on and a bunch of different things going on that we need to notice. There's never any one place that is necessarily the best place to start. So if you look at this question and you decide I want to start here instead of there, then go for it. That's totally up to you. And so what I want you to keep in mind is that anytime you see a straight line, the sum of the angles along that straight line need to add up to 180 degrees. And so that tells me where to start. Also, 140 is the only clue we have. So if the angle that we know is 140, and this full angle has to be 180, that tells me that x is 40 degrees. Or 180, take away 100. Okay, so x is 40 degrees. So that's going to be our starting point for everything else. So I'm just going to erase that part. And I'm going to color in angle x. So that's angle x. And it has the arc AD. So now I'm going to look for any other inscribed angles that have the same arc, because they're going to have the same value. And so we have angle y, or angle ABD, and it has the same arc, so it is also 40 degrees. Okay? So those are the first two. Those two, once you know the 40 degrees, should be really easy to see. The next couple angles might be a little bit harder to see. So I want you to notice that C to E is a radius line. And any radius line on a circle is going to be the exact same. So that means C to E is the same length as C to D. We now have an isosceles triangle. So that tells me that this angle is also 40 degrees. And angle N is going to be 40 degrees plus 40 degrees plus whatever we need to make 180 degrees. Okay, so this is, here I'm going to go N. And so hopefully you can see that the missing piece is 100 degrees. So N is 100 degrees. If we went 180, take away 40, we would be left with 100 degrees. So N is 100 degrees. Okay, we'll do the same on for the other missing angle, missing M. Two ways we could solve it. First, we could say CDE on the arc BE. We know that this angle was 40 degrees. I just erased it. Go back if you don't believe me. And we have another inscribed angle on the same arc, angle M. And so angle BDE equals angle M, and they both equal 40 degrees. We could have also used the isosceles triangle to help find the missing angle. The last angle we need to find is angle C, or the central angle. And so the central angle is always twice the inscribed angle that is on the same arc. And so if angle M is 40 degrees, that means angle C has to be 2 times 40 degrees. So the central angle is 80 degrees. Okay, these last three might look a little bit tricky, but I do want you to give them a try. Again, I'm going to give us 1 to 1.5 classes to work on this. So if we need to sit down tomorrow together and go over things together, then we will do that if necessary.